start. Enough people already tried.
Okay. So the title of this work is Computing the Similarity Between Algorithms. And this work is inspired, here we go, by machine learning models that generate source code. So of course, these are becoming increasingly common. There are all sorts of different machine learning models of code that are being used in various ways. So if you have one of these machine learning models of code, you're developing one, or maybe you're trying to evaluate an existing one, there's a lot of questions you might be interested in asking. So you might want to know, is the generated code correct? And if it isn't correct, how close is the generated code to becoming correct? You might want to know what level of quality are the identifier names. This would be especially important if this code has to be maintained by human engineers in the future. You might be interested in how efficient the code is, and so on. So you can answer these questions by just sort of looking at the output. But doing a rigorous human evaluation of machine learning model output is typically very time consuming. So what people do instead is they've developed techniques to automatically evaluate the output of machine learning models, which makes iterating on developing these models a lot easier. And generally, this evaluation falls into kind of all the same sort of schema or format. So the machine learning model generates a prediction, which we call the generated code, and then that's compared against some sort of known correct solution, which is called the reference code. Now, of course, machine learning models of code have existed for a long time. So there are a number of existing metrics to do this. But unfortunately, none of these metrics help us answer any of the questions we asked previously in particular. Another way of saying this is that none of them really measure any aspect of similarity in particular. So for the purposes of demonstration, we'll take a look at blue and crystal blue. Blue is one of the oldest metrics. You'll see it in a lot of some of the older literature. Although there's been, more recently, there's been some complaints that it's a sort of a weaker metric. Crystal blue is a more modern update. I believe it was released at ASC last year, ASC 2022, which makes a few adjustments to the way that blue is calculated to try to improve the performance. But both of them are based on the principle of calculating the sort of token overlap or subsequence overlap between the generated and reference code. So we'll take a look at what this might look like. So here's a hypothetical piece of generated code, and here's a hypothetical piece of reference code. And just for simplicity, we'll take a look at just a few.
No, okay.
Was there a question?
Yeah, sorry.
No.
Okay. All right. In that case, I'll
go on, please.
Okay, all right. Yeah, I'll continue. So we'll just focus on these particular subsequences just because for simplicity. Now, these subsequences occur in both the generated and reference code. So this is considered a good thing in terms of the metric. So the model gets points for these. However, these subsequences occur in the generated code, but not in the reference code. Or one of them occurs in the generated, but not in the reference, and one of them occurs in the reference, but not in the generated. So in this way, the generated code doesn't match the reference code, and this is considered bad. So these subsequences don't match. And the calculation is a little bit more complicated, but sort of the general idea is that it's the total number of subsequences in the generated code over the total number of subsequences. Usually the subsequence length goes up to like four tokens. Now, these metrics don't really calculate any particular aspect of similarity. They certainly don't measure correctness. I guess to see this, you can consider the fact that you can swap out the variable names and well, leaving everything else the same. And the functions, the blue score may change depending on your tokenization, the size of the variable names, stuff like this. it doesn't really measure variable name quality either, because there are other syntactic details that are sort of factored into this tokenization. It certainly doesn't measure efficiency in any way. So it doesn't really measure anything in particular. And instead, it's kind of this arbitrary heuristic measure of similarity. And sort of the discrepancy between what a researcher feels that correctness, that a high degree of similarity should be, maybe they're indicating correctness or something like this, is the thing they're trying to measure, and what these metrics actually measure is one of the things that motivates the creation of new metrics. So as an example, a CodeBird score released earlier this year is the newest on this list. And this is the motivating example from the CodeBird score paper. You can find it on page 2. So what's going on here? Well, the reference code is basically an implementation of the common index of method. Part B is an implementation of a contains method that's done with a similar for each loop structure. And then part C is also an index of method, just using a normal Java for loop. So the authors of CodeBird score argue that CodeBird score is better because it, at least for this example, CodeBird score rates the index of function, part C, as more similar to the reference index of function than it does the candidate, the contains function, as similar to the reference function. Whereas Blue and Crystal Blue, the metrics we previously looked at, do the opposite. They rate the contains function as more similar to the index of. So sort of the explicit claim here is that CodeBird score is a better metric for measuring code similarity because it rates semantic equivalence more highly in its notion of similarity. Kind of the implicit claim that the authors don't make is that equivalence is the measure of similarity that is most important, and therefore that is what code similarity metrics should be measuring. Now, and I think in many cases that is actually something that's really important to measure, because after all, if your the code produced by your machine learning model is like really high quality and really efficient, it's like easy to maintain, but it doesn't do what you want it to do, it might not be very useful. So, and then even further on top of this, if your machine learning model doesn't produce something that's semantically equivalent, but it's like pretty close, that would be good to know as well. Maybe you're iterating on developing a model and you want to see how much better you're getting. Or if something's close enough, a human engineer can go in and just make the required few little changes or something. I know people who work with GitHub Copilot report to have done this. So the thing is mostly right. There's a few little changes they need to make, and that's still useful. So this notion of is it correct, and if not, how close, would be really great to have. But unfortunately, this is undecidable in general. Code equivalence is undecidable due to the halting problem. And unlike a lot of really hard problems in computer science that have good approximate solutions, this one doesn't. Approximating code equivalence is just really, really difficult to do in general. To illustrate this, CodeBird score, the metric we just looked at, is better than existing metrics at measuring code similarity. But the authors do an experiment to sort of gauge correctness in an approximate way. So if they have a set of unit tests for every function, and if the prediction passes all the unit tests, they say it's correct. So this is a reasonable approximate notion of semantic equivalence, but the Spearman correlation with this test-based notion of correctness is only 0.395, which is generally interpreted as kind of between low and weak correlation. So kind of in summary, code equivalence is a very, very difficult problem to solve. Sort of a more realistic proxy for that's relevant for some machine learning tasks is algorithmic similarity. So if you look up the definition of an algorithm, it's like a finite sequence of operations that's used to perform a given task or something along these lines. So we could say that two algorithms are identical if they perform the same sequence of operations. But this is actually a little bit too strict. We can soften this definition a bit. Take a look at these two functions here. So you can clearly swap the first two lines, and these two always end up computing the same result. So, sorry, the train is going by. I'll stop here for a moment. Is it done? I think so. Okay. So in fact, both of these reduce to the same flow graph, which it's a little bit easier to see that these two are the same algorithm. So we can soften this and say that two algorithms are identical if they have the same partial order of operations. So algorithmic similarity, why do we care about this? Well, it is relevant for a number of different machine learning tasks. So transpilation, where you take one programming language and translate it into another one. You'd expect it to be the same algorithm, just in a different programming language. Neural decompilation is something where you take an executable program and convert it to the original program, to something that looks like the original program. The algorithm should be encoded reasonably well at some level in the binary, because the binary has to run. So this is another use case for algorithmic similarity. And then for automated refactoring, you are attempting to transform your code in a particular way that should be predictable. So these are all examples of tasks where algorithmic similarity is very relevant. So we've developed a tool called CodeAlign, which computes a very useful proxy for algorithmic similarity. There are a few little asterisks on this where this is not 100% algorithmic similarity, but it ends up being pretty good in practice. So what CodeAlign does is it finds similar computations in similar contexts. So take this example function, and then we'll compare it to this other function. And then further, let's consider this logging statement. So if we compare this logging statement with this list comprehension, these are just completely different computations. They do very, very different things. So we never say that these are really the same in any way. Now, if you take, where's the arrow? Well, you get a bit of a spoiler for the next animation. If you have the second lower logging statement, the one in red, you have the same computation, but it exists in a different context. So they're both logging things, but they're logging different things. Then if you look at the top logging statement, these are the same computation and they exist in the same context. So they're both logging things and they're both logging the same thing. That is, they're both logging the first argument to the function. So this is a useful notion of similarity, but it's not immediately evident how to compute such a thing. So the way we do this is inductively build a mapping between like operators in similar contexts. Okay, that is a lot all at once. So let's unpack this sentence a little bit. So first we say it inductively builds a mapping. What are we mapping together here? Well, in this case, operators that occur in similar contexts. So here we haven't specified a way to compute this, but it's kind of obvious that the two plus operations in the generator and reference do the same thing. So we would map these together. We say that these operators that map together are aligned, hence the name CodeAlign. And in particular, we only map together like operators. So operators that do the same same computation. So here we have this plus operator and this foo operator. These two things in general do different things. I suppose foo could be a wrapper for plus when we don't necessarily know that. But in general, plus and foo will do different things. So this mapping is illegal. We would never do this. And then finally, we do this inductively. Induction implies the existence of some sort of base case and then some sort of inductive step. So there's a number of different possible base cases. First, equivalent constants. So if you see the same constant in the generated and reference code, these two things are, of course, always going to be the same. Parameters. We consider parameters equivalent if they occur in the same position in the function's argument list. We ignore the names of the parameters, so we ignore the author's intentions in what the parameters should be, and instead we consider what would happen if you pass the same values to the parameters positionally, kind of ignoring those intentions as communicated by variables. Global variables with identical names are considered part of this base case. And then this one has a little bit of a subtlety to it, but basically functions with no arguments are also part of this base case. And then our inductive step. We say that two operators may map together if at least 100 alpha% of their arguments also align for some user-defined alpha. So basically, this alpha is measuring how similar the arguments of two operators have to be considered aligned. So if we have this foo function, one of the generated, one of the reference, in order to align these two, we have at alpha equals 1.0, A would have to be aligned with C, and B would have to be aligned with D in order to conclude that the foo function aligned, a generated foo function aligns with the reference foo function. But if we lower alpha, we can soften this condition. So at alpha equals 0.5, or actually less, only 50% or less, if alpha is less than that, will of the arguments have to align to conclude the conclusion. So we could not satisfy the condition that B equals D is aligned and still align the foo in the generated and foo in the reference. So let's take a look at what this looks like. Here's an example pulled from one of our experiments. So the generated code is produced by a machine learning model, and the reference code is the correct answer. Now, there are some meaningless syntactic differences, but there is one semantic difference that is particularly meaningful. In the generated, the result of getChar is not assigned to the variable C, which means that when C is compared to end of file, the C not equals EOF statement, that C is actually just uninitialized memory. Whereas the reference does this perhaps in the proper way, where the value is assigned to getChar. So it's that character that's being compared to the file. So a bit of a subtle difference here. Let's convert this into a more convenient form, so this data flow graph form. And it's a little bit easier to see that here we have this uninitialized memory, and in the other case we don't. It's actually using the results of getChar. Okay. So let's do some induction. So here we have the generated reference code, start out with our known facts. And we say that any two pair of like operators, so operators that compute the same computation, can be considered aligned. So we can start out with these two, because these two are both the same thing. They're both not equals. So let's compare their arguments. Is uninitialized memory the same thing as getChar? And is end of file the same thing as new line? Well, the answer is, of course, no. So we don't satisfy the conditions of this lemma here, and we really can't conclude anything. But how about these two? Well, getChar is the same thing as getChar, and new line is the same thing as new line. So we can, in fact, conclude that the first not equals is in the generated is aligned with the first not equals in the reference. So we can satisfy the conditions here and add this to our list of known facts. All right, let's keep going. So how about these two? Well, end of file is the same thing as end of file, but getChar is not the same thing as uninitialized memory. So what we do here depends on our value for alpha. Now, normally you define this before you started. I explicitly didn't, just for the purpose of demonstration. So whether or not we can continue depends on this alpha value. So if alpha equals 1.0, we can't do anything because we haven't satisfied the conditions. And in fact, if you look at this, we really can't do anything else from here. We're actually done. We're stopped. But if alpha is 0.5 or less, we can satisfy these conditions because we can kind of ignore the fact that get char is not the same thing as uninitialized memory and conclude that the second not equals in the generated aligns with the second not equals in the reference. And then we can keep going. So both of the arguments to these functions exist in our, to the and function exist in our list of known facts. So we can add that, and then we can do the same thing for this while. Okay. So the immediate output here is a list of operators that map to each other. So if you wanted a really, really detailed picture of sort of the strengths and weaknesses of your machine learning model, you could try to mine a collection, assuming you did this over like a whole test set, a collection of these for patterns and see where your model is struggling and where it isn't. But often it's convenient just to have a single number that kind of summarizes this information. So we have just a really, really simple metric called align score, which is the percentage of aligned operators. So for this example, at alpha equals 0.5, the align score is 1.0. All the operators align with each other. And the way to interpret this is that barring some minor mistakes, the structure of the two algorithms is basically the same, or is identical here because it's 1.0. But at alpha equals 1.0, which is the strictest setting, we can see that the align score is not 1. So that means that there's some mistake in there that prevents the algorithms from being the same. In this case, the mistake is that subtle little, it's missing the equal C, that subtle thing. So one of the takeaways here is that by varying alpha, you can get a more detailed picture in terms of this number than you can with a single number. So you can show that the data flow graphs are the same at alpha equals 1.0 if the align score is 1.0. This is a fairly strong indicator that these two functions are semantically equivalent. There are some very subtle cases where this is not the case, but generally, if the two data flow graphs are the same, that's going to be true. And if alpha is less than 1, you can see how close the structure matches, kind of ignoring some minor mistakes. All right, so this is kind of the basic idea. There's some more complicated stuff. That's the second half of the talk, but I'll stop now, maybe for like 10, 15 minutes, and see if there are any questions.
Oh, hello, and thank you for the first part. It was really interesting. My name is Mishania. I have a question because so I be devoted to the rigorousness of this approach because it seems to be theoretically possible to prove a theorem that those two algorithms are actually equivalent and produce the same output. But it's kind of, I understand that it might be complicated using some formal languages like COQ or something like this. Is it so? Is it kind of how rigor is your algorithm?
So what this does is it shows that two data flow graphs, actually, these are, we use a single static assignment SSA form of the data flow graphs, which are a little bit more detailed, is it shows that those things are isomorphic.
Does it imply that you can actually prove? So is it kind of a proof that those algorithms are identical, or there might be some subtle cases, as you mentioned, that there are some subtleness?
So I it does not show that two algorithms are exactly identical. There is some control flow information that is not factored into the single static assignment form, where two algorithms can differ. Another thing we kind of hand wave here is types. So the example there was in C. If you had predicted we had int C, so C was an integer, but you could have char C. The data flow graph doesn't recognize types as well. So there's lots of little things like that that are different. So it is not a proof that two algorithms are exactly the same or equivalent. We haven't done a formal proof, and I'm not a I actually do a fair amount of machine learning stuff, and I'm not really a formal methods person. It seems, I think this is a proof that two subgraphs are isomorphic, but I am going to hold off saying that for sure, because I don't know if there's some subtle thing that I'm missing.
But just generally speaking, it is a strong indicator that they kind of might be identical algorithms.
Yes, very much so.
Thank you.
Alexander has raised their hand.
Hi, my name is Alex. Thank you for describing the solution. I have two questions. One is about runtime complexity of graph isomorphism kind of problem solution. And the second one is what kind of tooling would this approach require to extract the data flow graph and the representation that you are using? I would imagine it's some kind of, like with example of C you gave, maybe that's LLM or some part of compiler infrastructure.
Yeah. So the runtime complexity in general, determining graph isomorphisms is NP hard. We use a trick taken from some code clone detection literature, which is actually in the second part of the talk. But we use a trick taken from some code clone detection literature to reduce this substantially in practice. The trick, actually, we've kind of talked about it. The trick is that two that only like operators can possibly be aligned. So the only combinations that we have to consider are like operators. And typically you have a distribution of different operators in any given function. So the number of combinations you have to consider is substantially reduced. The running time of this it depends on the experiment. Some had like bigger graphs than others, but it's in the hundredths of a second. So it's reasonably fast. As far as tooling is concerned, to get these data flow graphs, I actually just wrote something from scratch. I have my own little Python object model. It's a big chunk of code. But another thing you could do, so we wrote the tool to work on C and Python. If you wanted it to just work on C or C++, LLVM compatible languages, you could probably just use LLVMIR, which maybe would have been a more efficient choice for me to have done instead of writing my own little. We use a library called tree sitter for parsing, but basically it's kind of equivalent to, we generate an IR, so it's kind of like code generation. I wrote that, and then I wrote the analysis routines that convert it into SSA form, and it does copy propagation, a few other things.
Really cool. And I think you learn so much more by doing that yourself at least once than reusing.
Oh, yeah, for sure. Yeah, it was great. All right. Danny.
Yeah, look, thanks. This is a very nice talk, and I enjoy your example. And so it seems to me, if you are using the language of code clone detection that you mentioned, that your approach is very good for type 1, type 2, and type 3 code clones, right? If the generated and the reference algorithms, you consider them a clone, or trying to think about them as clone of each other. So you are using already alpha renaming, so you do type 2, you are using the data flow, which gives you type 3. What are your plans for expanding, or are you thinking about expanding to type 4 clones, where now the syntactic structure is completely different, algorithms are identical, they are semantical equivalent, but one of them is using one structure, least comprehension, and the other one is using loops to do the same thing? Or are you guys thinking to expand to that level, to the next level of type 4?
Yes, so I've done some thinking about this. Actually, for the list comprehensions, we apply sort of this canonicalization step. So I convert list comprehensions into a for loop that with an append. But like in general, yeah, if you have a loop versus recursion or something like that. Of course, type 4 clones in general we can't handle. There's a number of possible things. One thing already exists, which is CodeBird score. But of course, CodeBird score has is very capable, but has some issues in that. Well, as we see, it's only weakly to moderately correlated with correctness, and the outputs. The quality of your score depends on the quality of your BERT model. And the output score is meaningless by itself. It's only meaningful compared to other CodeBird scores produced by the same BERT model. But CodeBird score kind of does do type 4 clones. Something I have thought about is trying to do CodeBird score on a smaller scale to measure similarities of smaller fragments. So if there's some parts of like maybe like setup and tear down for the algorithm are like algorithmically the same, but maybe a loop is different. You try to use this for the setup and teardown, but then the loop you try to use something like CodeBird score. There's a lot of details that are missing from there. I would have to spend some time actually looking at that, but that's one idea to try to take on some type 4 clones. Yeah,
because especially in the scenario that you gave with LLMs generating code and stuff like that, they are so creative that very likely you are going to result. So I wonder, maybe you show in the next part, when you generate actual codes, and are they generating most of these, type 3 clones, or you are running into type 4 clones quite often when you're comparing generated code from LLMs with reference codes?
So it depends on the task. So this thing, I guess another way to say this is this thing always measures algorithmic similarity, but whether or not you care about algorithmic similarity is something else. So there's I had a slide a little bit earlier, but there's I listed a number of tasks. In those tasks, you expect and you actually want the output to be algorithmically similar to the reference. Like that is what you want. In other tasks, especially where you give the model freedom to be creative, like natural language to code type tasks, algorithmic similarity might not be something you care about that much. You just want it to be equivalent to the reference, but you don't care if it's equivalent by computing the same thing in the same way. So in that case, so we tried this. Our score does actually the sort of way I found out about this was I talked to Misha about his paper earlier this year called Out of the Blue, where they compare a number of different metrics on natural language to code things, and we found this does okay. It doesn't beat any of the existing metrics. It's kind of average. I did those experiments. We don't talk about them in the paper because that's not really a strength of this work. But so I can't remember what the numbers are. But it's okay. And the failure cases are when failure cases, because it's always measuring algorithmic similarity. But when algorithmic similarity is a thing you don't want to measure, is the cases where the LLM gets too creative. And it does something in a completely wild way, and we just, well, the human intuition is, oh yeah, those are the same. semantically, it's a type 4 clone, basically, yeah.
So I guess a natural question here is, did you compare your metric to code blue? Because, okay, we have lexical metrics like TRF, we have embedding metrics like code score, and yours would be in the league of Ruby and code blue. Did you compare your metric performance to these two?
So code blue is interesting. It has kind of 4 components, some of which are, so some of it is lexical, some of it is like a keyword overlap. Some of it is an AST overlap, like they do kind of like blue for subtrees. And then they have this overlap between, the paper says it uses the term data flows, which I'm not entirely sure what that means. From context, I think it means edges in the data flow graph. They do some sort of like overlap between those. So it's all very heuristic. I guess it's not as rigorous as, and I don't want to use the term rigorous because again, I'm not a formalist methods person, so I can't make any strong statements. But it's not as rigorous. It's a lot more heuristic. Code blue in that way doesn't really measure anything in particular either. So it uses a different set of heuristics, but it doesn't measure this. So when you say, did you compare? I'm not sure necessarily what you compare it against. You could compare it with some sort of like notion of human similarity, but those human notions of similarity, I guess unless the humans were asked to say, are these things algorithmically similar? Are these things semantically similar? Human similarity scores can also be kind of a mix of different notions of similarity as well. So I've looked at some of them where like, I thought like, oh, those aren't very similar, but they have a high human score because they have similar names, or I think those two are similar because they have a high semantic equivalence, but somebody rated them lowly because they have different API calls that do similar things. So I'm not sure how I would go about evaluating that, but I guess the short answer is no. But there's a reason why.
You just mentioned that you tried to evaluate, if I got it correctly, that you tried to evaluate against human input, and you got medium results. But then, for what I recall, code blue was quite bad, and I think Ruby was not too good. So maybe, I mean, if you clear the bar of being better than code blue and Ruby, that makes metric more interesting to try when you're trying several different metrics, like lexical, algorithmical, and I don't know, embedding, for example.
Oh yes, I see what you're saying. Yeah, it could be used in that way. I guess, yeah, we kind of dropped that experiment from the paper. So I did this a few months ago, so I can't remember the numbers too well. But it did okay. It didn't do amazingly well because of those failure cases. But that is, yeah, correlating with the human notion of similarity. But what a human notion of similarity is kind of arbitrary as well, in a way. But yeah, it certainly could be used in that way. That's something we don't talk about, but we could.
Okay. Any other questions, folks?
Oh, yeah. Just maybe a quick idea about formal proofs. If you have, for example, 2 algorithms that you know that are equivalent by proof, you can compute the metric on it and say, well, it's well correlated with the proof. So if this is proved, then the metric is high. If it's proved that they're different, for example, if there are some existing algorithms that can be compared and they're proved to be identical, you can just validate the metric and say, whoa, they are both high and they are both low in such cases.
That is a good idea. Yeah, I like that. I didn't think that, but that's a really good idea for an evaluation experiment. Thank you.
Thank you.
Okay. I guess, unless there are any more questions, we'll move on to part 2 of the talk, where it gets more complicated. So have a slide for that. Unfortunately, it gets more complicated. Here's an example of some hypothetical generated code and hypothetical reference code. It's kind of as a motivating example. And these two are exactly identical. So we would expect that these two align perfectly because textually they are completely identical. But given the algorithm that I presented in the first half of the talk, we end up having a problem. And the problem has to do with these code fragments. So this is a little bit of a, these two functions create a bit of a big data flow graph to actually put on a slide. So the data flow graph I'm going to show for this only contains these parts. And it looks like this. So let's go ahead and do some induction. So we can start just as we've done before. So we have the dots here are attribute accesses. So this is Python. So we're just doing like con.readable is what's what this first thing is. So the first attribute access operator is we'll compare that in the generated with the first attribute access operator in the reference. We can do that, of course, for both attribute accesses, and then we can look at the arguments. Con is the same thing as con. Readable is the same thing as readable. So we can conclude that these two are the same. The conditions are satisfied, and add this to our list of known facts. Great. Let's keep going. So we have these two. Well, these are both attribute accesses, so we can compare their arguments. Con is the same thing as con, and readable is the same thing as readable. Yeah, we satisfy the conditions, and we can add this to our list. And then we can keep doing this. So maybe you can see where this is going. These two are both attribute accesses. All the conditions are satisfied at any alpha, so we'll add this, and then same here. So we've run into a bit of a problem. And it's something that we call conflicting operators or conflicting mappings. So we say that two operators conflict if one operator in the generated aligns with multiple operators in the reference or vice versa. So if you look at the sort of the column that we have here, using the convention, of course, that generated is on the left and reference is on the right, the first attribute access in the generated aligns with the first attribute access in the reference, but it also aligns with the second attribute access in the reference. Thus, and kind of, if you just use transitivity of equality, this says that the first attribute access in the reference is the same thing as the second attribute access in the reference, which is a bit weird. So you have two separate operators that are actually the same operator. And between these four equivalences, you have lots of these little conflicts within. Now, is this really a problem? Like, after all, con.readable is con.readable. So maybe that's not a bad thing, right? Unless con.readable was modified. In this case, it isn't. So we could just consider all these aligned with each other, consider it the same. In general, you can't do this. This isn't sound for operators with side effects, such as read. And this works very, very poorly when alpha is less than 1. So we don't want to do this thing where you can have operators, two operators be considered in the generated reference, or two operators in the reference be considered the same thing. So what we do instead is we differentiate these operators based on future information. So what this looks like is this. So we see that the first attribute access in the generated reference are each passed to the tuple initialization operator, whereas the second attribute access in the generated reference are each passed to the if statement. So this is some useful information we can use to differentiate these different attribute access operators. But unfortunately, just this insight doesn't give us a mechanism for how to do this. So the mechanism that we use is code clone detection. So we use clones to incorporate future information about operators. So we define clones in kind of a type 3 clone way, if you're familiar with code clone detection literature. We define clones as isomorphic operator subgraphs which respect operator ordering. Operator ordering being like arguments to a given operator must be in a specific order. You can't, in general, switch the arguments of an operator and expect them to be equivalent. we're going to define the term isomorphic here to include that the fact that nodes that map to each other must perform the same computation. So just as we've seen before, so plus and plus can be mapped to each other, and plus and minus cannot. Another way to think about a clone in this context is that it is a generalization of operator mapping. So an example of a single operator mapping that we saw before is the ampersand. The AND operator is the same as and the generated is the same as the AND operator in the reference. In this case, a clone can consist of multiple of these things inside a single clone. Now we build clones using a fairly old method, but it works very well in this case. We initialize them with single potential mapping, and then grow them recursively by considering those mappings arguments positionally. So let's take a look at what that looks like. So, for example, we will start out with this tuple initialization operator. So, of course, tuple initialization is the same operation as tuple initialization, so we can start out with this pair. And then we'll look at the first argument to the tuple initialization operator. Now, one of the things that we do is we only operators can be part of clones, sort of implied part of the definition. So DH, this variable is parameter is not an operator, so it doesn't satisfy these conditions, and we don't add it to the clone. But for these, looking at the second arguments of tuple, this attribute access is an operator. Of course, attribute access is an operator. Attribute access is the same thing as attribute access. So all these conditions are satisfied, and we can add this to our clone. And then we can do the same thing for this. Of course, the third attribute access is an attribute access. Third attribute access is an attribute access, so on. So these two, we can add this to our clone as well. Now, we said we do this recursively. So we've run out of arguments that for tuple to have, but we've added some other operators to our clone. So we need to consider their arguments as well. So we'll add these arguments, the first argument of the first attribute access, but of course both of these are not operators, it's an argument, so these conditions aren't satisfied. And then of course, I won't step through the rest of it, but you can see all of these others are not operators, so we won't add anything else to it. Now, if you do this for every pair of like operators, you end up getting 8 clones. So in the example, we just generated clone 0. There's also clone 1, which we recognize should exist, but there are also 6 other clones that exist that happen when you initialize with different pairs of like operators. Now, if you look at this, you'll notice that some of these naturally conflict. So clone 1 and clone 5 conflict with each other because they both contain the operator, the second attribute access operator in the generated code, but they map it to different things in the reference code. So this is a bit of a problem. We created clones to deal with these conflicts, but we still have some conflicts. So we get rid of conflicts in one of 2 different ways. Now, a useful thing to think about when you have clones is you can kind of think of clones as compound operators. I hesitate to use the term function because function is kind of overloaded in this context, but you can think of them as like their own mini function as well. And the arguments to a clone are all the incoming edges, incoming data flow edges to that clone. So using this insight, we can realize that we can just apply inference. And in doing so, we can prove that some clones are true based on context, and some clones aren't. So for clone 1, con is always the same thing as con, and readable is always the same thing as readable. So at any alpha we pick, this is going to be true. But con is, for clone 5, con is always the same thing as con, but readable is not writable. So we can't satisfy these conditions. Now, if you lower alpha enough, and if you in particular you lower alpha to be less than 0.5, you can satisfy these conditions as well. But we say we have a rule in our algorithm that if you have a conflict, the clone that can be shown at a higher alpha level is the one we select, and we discard the other clone. So this would allow us to discard clone 5 in this case. So we can eliminate that from contention. And we can do this with all of the clones. So here's a list of every single clone, all the lemmas we would need to show them in this example. And if we do this for all of them, we can discard, in this case, exactly half. In general, it's not half, but this case we get rid of half of the clones. So we've eliminated some of them. So kind of our roadmap of what we've done so far is we generate a bunch of clones, but then using induction, we can show that some of them don't make sense in this context. So the proven clones are going to be a subset of the generated clones. But if you look at the proven clones, we haven't actually solved our problem yet. There's still more to go because both clone 1 and clone 2 were shown on that previously, but clone 1 and clone 2 conflict. So you can see that here they both, and in this case, the second attribute access operator, but in the reference. Sorry, what was that?
Oh, sorry.
Okay. Code clone. So clone 1 and clone 2 conflict on this second attribute access operator in the reference. So wait a minute, we haven't actually solved the problem. If you recall, actually, the original problem, the original motivation for this was that the first and second attribute access operators were conflicting. So we're kind of back to square one, right? And in fact, if we recall this slide from earlier, we recognize that future information can help differentiate conflicting operators. But now we have a mechanism to do so. So this clone abstraction can help us do this. So we do this in a very systematic way by modeling the clones and their conflicts as a system of linear equations. So here we have the generated and reference code, and then I'll highlight in particular code clone 1 and 2. We know there's a conflict between those, so we'll just focus on that conflict. There are other conflicts here. So what do these equations mean? Where do they come from? Well, let's look at this one in particular. And what this says is clone 1, so we assign every clone a unique variable. We say that clone 1 conflicts with clone 2 on operator, the second attribute access operator in the reference. And further, only one of them can be assigned that clone because only one of them can be assigned that operator. Because if more than one were assigned that operator, they would conflict. Now we constrain each of these variables to be either 0 or 1. It's kind of a Boolean thing. Of course, you can't have something be like partially in a clone. That doesn't really make sense. So it's either in the clone or not in the clone. And of course, a way to generate these equations is for every operator. If a clone contains that operator, you add that clone's variable to the corresponding equation. So you have one equation for every operator. That's how I've organized them here. And then you get this nice system of linear equations. Then if you solve this system, you can resolve the conflicts. So the solution, if you go plug in the numbers and do some substitution, the solution is this. So clone 0 is part of our solution, clone 1 is part of our solution, and the other conflicting clones get dropped off. So this is kind of what clone 0 and clone 1 look like, and as we can see, they don't conflict. So we finally solved the conflicts problem, which means that we can achieve perfect alignment here as we expected, because of course these two are exactly identical pieces of code, so we should be able to align them perfectly. So kind of a summary of what we've done is we've generated some clones, then we used induction to eliminate some of them because we can only prove some of them. But some of the proven clones nonetheless conflict. So we have this conflict resolution phase where we discard discard some conflicting clones, and then we finally end up at a solution. So kind of a summary of everything. The clone detection approach is a more complete version of the original inductive approach. So it can handle conflicting operators, whereas the previous version cannot. Operator mappings inside selected clones become the operator mappings for the function as a whole. So if we can compute clones are just lists of individual operator alignments. So you can just, once you've shown things are sort of done this proof with clones, you can just unwrap the operator alignments inside the clones, and then you have your final. This clone-based version of code align has the same advantages of the original version. So at alpha equals 1, align score equals 1, this means that two functions have identical alignments. And then by varying alpha, we can get a better picture of how well the two algorithms align, or how similar those two algorithms are. I might have gone kind of fast with that second part. That is the end of part 2. So I'll again open it up for any questions.
Okay, thank you very much, Luke, for the talk. So yeah, at this moment we are right 1 hour past the beginning. So questions, folks? Anyone?
Look, it's me again. How do you evaluate how well does it work? Do you have some
Yes,
evaluate this empirically, analytically, or?
we do. So the way we evaluate this is, maybe I should have some slides for that. I don't. We do we have 2 evaluations. We have some sort of an artificial precise evaluation and a less precise, the kind of more real world evaluation. So the artificial evaluation is based on something called mutation analysis. So we take a function. We use the Python standard library for this just for convenience. It doesn't really matter what it is. So we take a function and we align it with itself. So of course this should align perfectly. But then we copy the function and then mutate it. So we change one operator in the function. Now we know which operator we've changed. So we would expect that in a perfect case, the changed operator to not align with something in the original code, but all of the other operators which we didn't change to align with something in the original code. And then we measure, we kind of compute an F1 score for how well we've done this. Then we repeat this process. So we take the mutated function and then we mutate it again. So it has 2 mutations. And we do this up to 10 times. And then measure how good the alignment is. So we've kind of, it's kind of like, what's the term? Like masked language modeling, in where you take from some unlabeled data, you create labeled data and use this to evaluate the metric. So that's kind of the precise analysis. The imprecise analysis is we use it for deduplication. So of course, this is also relevant for training machine learning models of code. There's some existing work out there that says if you train a machine learning model on duplicate copies of source code projects, that machine learning model will perform a bit more poorly. So it's best to have a deduplicated data set to train on. Now, the tricky thing with deduplication is oftentimes what people will do is to like clone a popular GitHub project. In the past, I was training an ML model on C code, and the number of clones of copies of Linux is just incredible. There were so many copies of Linux in our data set. But the thing that makes this really tricky is that people will have people will like download a copy of it and like make a few small changes and then push it up to their personal GitHub repos and then like never change it. So you have a lot of different slightly modified and different versions of the same project in a data set. So you can't deduplicate entirely with like just text, just doing a string comparison. Because if you did that, you'd miss the near duplicates, which are pretty common, just from having different versions of the same project. So we devised an experiment where we use this to deduplicate a data set. We take some very high GitHub star projects, and there aren't a lot of duplicates among high star projects, and then intentionally duplicate them by checking out a random commit hash. Then we use this to see how well code align detects the duplicates that we intentionally put in. So it's, again, we're kind of creating labeled data from some unlabeled data. So we use this to evaluate how well code align works. Then we have an additional experiment where we show the utility of code align using on a neural decompilation task. Any additional questions?
I have a question. Can you hear me?
Yes, I can.
So hi, thanks for the presentation. So I followed. I remember you mentioned a few competitors in the first slides, and there was this BERT score, if I recall correctly. Code BERT score, exactly. And then you mentioned this Spearman rank correlation coefficient with respect to the test suite execution, right? You said it was weak or low.
Yes, it was. It's on like 0.4, 0.38, 0.4 is considered. Below that is weak and above is moderate. So it's almost like on that borderline between weak and moderate. But yeah.
Yes, so my question is whether that evaluation setup can also apply to your approach. So whether you could run the same and get another number and see, I mean, how well it compares. Does it make sense or it's not always possible?
It makes some sense. So this thing will, this is just an inherent limitation we know about this technique. If you have what's called a type 4 clone, so two things that are semantically identical but done in completely different ways. Like one uses a list comprehension with an if statement, and another one uses like map and filter in Python.
Mm-hmm.
So these things are equivalent, but they are different. Different syntactically. We will not detect that. We will rate those things as completely non-equivalent, whereas they actually are equivalent. So if we were to run this experiment, we certainly could. I would expect the scores to be relatively poor, depending on the composition of the data set. How many of these predictions are algorithmically similar and how many of them are not algorithmically similar and semantically identical. Sort of the ratio of that will determine how well we do on that data set.
Yeah, makes sense. So I asked this question because one of my colleague, he worked on Crystal Blue. So I was wondering whether you did have a metric that compares directly with those. So, but I don't know, maybe you have other, because the setup you described seemed to be applicable to your case. I don't know if you also applied to the others and how well do they perform. Yeah, so I was curious about that. Thank you.
Any other question, folks? Okay, I guess I have some. So right, first thing that I wanted to ask. So basically, the point that you're making and the point I kind of agree on with you that just agreeing with humans is not enough. So do you have any idea on what scale should we evaluate a language model? Like, what should we check in it? We have some output, so what do we want from this output? What our metrics should measure?
Right. I guess so sort of the thing I was I guess kind of the point is that when you say like, is the output similar to the reference, or how similar is the output to the reference? That isn't sufficient because similar is a bit too general. It doesn't mean similar in variable names, doesn't mean similar in algorithm, doesn't mean similar in input-output behavior, similar in side effects. Similar is just kind of too broad of a category to really characterize the output well. There's actually something equivalent in the field of natural language processing. It's called multidimensional quality metrics. So instead of evaluating something just in terms of, is this translation of this French to German sentence equivalent to the actual German sentence? How close is it? They evaluate on things like, are the semantics the same? But then there's a different measure for how natural does the translation sound? So does it sound like something a native speaker would say, or is it like really garbled and hard to understand? There's kind of like something for idiomatic. Does it use, common phrases? So there's all sorts of different ways you can characterize a machine translation, as opposed to just saying, is this translation, how similar is this translation? Because it's a little bit too like, it's a little bit too general. There's lots of little subtleties. So that's kind of what we were trying to motivate here in this discussion. So you can have code that's semantically equivalent, but it just butchers the variable names. As far as I see, LLMs don't do that. LLMs like text, so variable names are meaningful to LLMs. So they tend not to do that, but they might do something in a very inefficient way. But there are all sorts of these different kind of aspects of similarity that you may or may not care about depending on the scenario. So kind of what we were trying to motivate is which aspects of similarity do you care about? Once you determine that, try to measure those. So something you could do with a human evaluation instead of saying, are these two pieces of code similar? You could say, are these two pieces of code semantically identical? Do they produce the same result for a given input? And of course, proving that in general is undecidable, but you can ask a human to do it and they can think about it and say, yeah, they are. Yeah, they are, or no, they aren't. So if semantics is something you care about, then you can do that. Whereas if you have a tool like GitHub Copilot, where it just needs to be semantically close because people can go in and fix it, maybe conciseness is something you care more about. So find a way to measure conciseness. And then maybe you also measure semantic similarity a bit, but you're not going to put as high of a premium on that. So it depends on the context. Like, what do you care about in your model output? Measure that.
Okay, I think I got you. So, I mean, my point, well, first of all, thank you for your treatment of this topic. And then I wonder, what would be the most broad set of things we should probably care about? Like, as you mentioned, I'm aware of these things when in NLP you measure like how natural this machine translation looks, whether it's something like native spec, stuff like that. So far we have like human evaluation, we have, I don't know, test-based, like whether it passes tests or not, 0 or 1. We have semantics. Do we need to account for something else? I guess something like code paratiness is reasonable, because if you only use one variables of 1 or 2 or 3 characters, it's not really readable. I know not what LLMs do, but still. But
right.
Do you have any ideas of what else do we want to measure in general?
So yeah, the list I gave at the start of the presentation was very incomplete. One of the first, or one of the sort of I don't know if it was actually, I shouldn't say first, I don't actually know the order of publication, but one of the canonical multi-dimensional quality metrics papers in natural language processing basically develops this very comprehensive taxonomy of different aspects of quality that you might care about in natural language processing. So I imagine you could do the same sort of thing here. I haven't built that taxonomy. Actually the motivation for this project was that we were working on one of the tasks under neural decompilation where algorithmic similarity is the most useful. So originally this was just designed for that, to evaluate that particular task. And then we recognized, oh, there are other tasks that have this property where you care about this very particular aspect of similarity. But not all tasks have this property. So the best thing to do, and this might be a bit more work on top of what I've done, because what I've done here is very heuristic and very off the top of my head, based on a single task, is develop a sort of a taxonomy of similarities, and then that would probably be a more complete and systematic way to do it. But I haven't done that.
Okay, thank you. Another question that I had, so okay, in the summary you mentioned that by varying alpha you can get a picture of how well do the algorithms match. So I wonder, does it make sense maybe to plug in several different values of alpha and average the scores in some fashion? Or maybe should we report several results in a row or something else? What would be your take on that?
So what we do is, so in the paper, we give an example of how this works under neural decompilation, the original task that motivated this. And we report several values of alpha and sort of contrast them. So kind of the summary for the neural decompilation results is that at low values of, so we do it for 3 values. We do alpha equals 1, we do alpha equals 0.5 and alpha equals 0.1. And we report values for those separately. So at alpha equals 0.1, the scores are really high. At alpha equals 0.5, the scores are still pretty high. There's not much of a change from 0.1. And then alpha equals 1.0, the scores are really low. So what this tells you is that it's good at predicting the structure. It's good at predicting things that are almost right, but it misses lots of little subtle things. And in fact, the first example that we went to with the uninitialized memories character thing was an example from the neural decompilation task. So sort of the pattern there, the fact that we got low alpha scores, but low alpha equals 1.0 scores, tells us that the models are generally good at getting structure, but they miss lots and lots of little subtle things. And actually the example we presented was kind of a representative example in that way. In that lots of little mistakes it makes that are just not quite right.
All right, thank you. One more technical question I got is about how do you do this from the technical point of view. So Alex already addressed that a little bit, but okay, my experience in comparing graphs was that, okay, we ran Ruby, which is also comparing data flow graphs at a certain point. And that thing is, well, NP hard, so we use some approximation from network X, and then it works like really for quite some time. It takes more than a second to evaluate one example, or otherwise you have quite decent risks that your results will be off because you're doing numerical computation. Something may go wrong and it's not even clear what's going on. So how did it work for you? How much time do you take for to evaluate one example? Like how does it change if you allow for more time for numerical computation, stuff like that?
So actually, this is quite a bit faster than that. It depends on the task, because different tasks had different size examples. In our deduplication experiment, for example, there's lots. The average Python function size is like 60 nodes or something. So those were really, really fast, whereas the neural decompilation examples were a bit bigger. But still, the average time, average and median time were in like the hundredths of a second. So like 0.01 to 0.09-ish. There are some that took longer, although the things that took longer was actually, let's see if I can, the extra slides, was actually solving this system of equations. We have two equation solvers. One of them that we use is Z3. There's a bit more complexity that I didn't get into. One of the equation solvers we wrote for this scenario, and it's really fast. The other one, we just use Z3, and Z3 is much slower. So things that take longer, they take longer because of Z3. Occasionally Z3's heuristics, I'm guessing, so because it's just an SMT solver. So usually it has some heuristics to try to make it fast, but in general it's NP hard. It just resorts to trying every combination, which is exponential. So I'm guessing what happens in these scenarios is Z3's heuristics fail, and it takes a really long time. The graph comparison is not actually a problem, because we take advantage of the fact that two different, we can only align two nodes if those nodes have the same operation, which substantially reduces the number of different combinations you have to consider, and thus we don't have to resort to any different approximations. We can compute things exactly. This approach works if you do this at the scale of a single function. This approach doesn't work so well if you do this at the scale of like trying to compare an entire code base with an entire other code base. But if you're just comparing one function with one function, the number of different combinations of like operators inside of a single function, even a big function, is small enough that it's fast.
Okay. Okay, thank you. Any other questions, folks? Okay, a couple more technical ones. So is your paper available now? And is your repo available now? Maybe as a Zinode artifact, which is non-attributable, but still.
So the code is not available. We've submitted that as an artifact. So the submission system from the conference had a place to like upload a zip file with your artifacts, and they had to be super anonymized. So I spent a bunch of time like making sure my username wasn't in any file path or something. So the code is currently unavailable. We'll make that available on publication. We currently don't have a preprint of the paper out, but we could do that. I could. Yeah.
Okay, I mean, just ask. I guess that's pretty much it for questions for me. Any other folks who made it till this time? Any questions from you? All right, so then thank you again very much, Luke, for coming to our seminar and presenting. Fingers crossed on your paper acceptance to FSC 2024. And I'll stop the recording now.